Welcome back to module 3. We have just discussed how a traveling Gaussian would propagate, and we have seen that the free particle, because we are discussing free particle without any potential, it is not experiencing any potential. So there is no potential, it means there is no force acting on the particle. Classically we understand that the particle would be all that traveling with a constant velocity. The similar thing we have seen in quantum mechanics. Particle in quantum mechanics would be represented by a localized matter wave. We should not view as a ball or a small dot in quantum mechanics. It should be a localized wave packet, and what we have seen that wave packet for the free particle is traveling with a constant velocity. That's the group velocity, the center of the envelope, how it's moving. And so this is a very nice intellectually stimulating discussion we had for the with an analytical solution for the wave packet dynamics. Next, what we'll do, we have been seeing that this is the form which we have got for the Gaussian wave packet and the particle. So the particle represented by this, so I had the wave function, this is the particle, and at different time I have this expression for the wave packet represented by the particle. Now this expression we will modify to a particular kind of expression, so that we can very conveniently use that for other problem. So that's why we are calling it is a general form of the Gaussian wave packet. We don't want to keep it in this complicated form. We will modify it to a form given by Eric Heller, who has worked significantly on this Gaussian wave packet dynamics, and we will reach that form to use it for our subsequent analysis. So we will just modify this. This is just a rigorous mathematical derivation we will be getting involved right now. So first we will look at this exponentiation part. This exponentiation part can be written as minus k naught whole square by 4a plus I kx minus I k h cut k square t by 2m. So this is the exponentiation we have, and we can simplify this as follows. This is k minus k naught whole square divided by 4a plus I k minus k naught x minus I h cut k square minus k naught square divided by 2mt plus I k naught x minus I h cut k naught square t by 2m. So in this form we have this is the way we are writing, and now we will use this identity. Identity is following: this k square minus k naught square. This can be written as k minus k naught whole square plus 2 k naught into k minus k naught. So this part we can write as, so k minus k naught whole square by 4a plus I k minus k naught x minus I h cut k minus k naught whole square plus 2 k naught into k minus k naught multiplied by t divided by 2m plus I k naught x minus I h cut k naught square t by 2m. It's just rigorous mathematical derivation, that's all. But we need this derivation to reach that final form, the general form of a Gaussian wave packet, which we'll be using for subsequent analysis. So what we'll do right now, this k minus k naught, this term will be represented by s. And if we have that, then the whole argument will be reduced to this minus s square divided by 4a plus I s x minus I h cut t by 2m s square plus 2 k naught s plus I k naught x minus I h cut k naught square t by 2m, which is nothing but minus s square 1 by 4a plus I h cut t divided by 2m plus I s x minus h cut t k naught divided by m plus I k naught x minus I h cut k naught square t divided by 2m. So this is the form we have got, and the reason why we are using this kind of form, it will be revealed very soon. So so now we will move forward and further reduce the equation as follows. We have now psi wave packet xt is going to be 1 by 2 pi 2a by pi to the power 1 by 4 square root of pi by a, and then in terms of s we have to represent the argument. Argument is following: e to the power minus s square 1 by 4a plus I h cut t by 2m plus I s x minus h cut t k naught by m plus I k naught x minus I h cut k naught square t by 2m, and this integration is going to be over ds. Here integration was k, so if we look at this k minus k naught equals s, so I can consider dk equals ds, because k is actually the average wave number component which we get from the after the interference. The origin of this creation of this wave packet was the interference of many components, the matter wave components, and if we take the average of all wave numbers, that is the k naught. So k naught is constant for a particular wave packet, and because it's constant we can take this derivative. So integration can be over ds, and that's exactly what we have done here. So the reason why we have reduced it in this form, because again we'll be able to use the standard Gaussian integral. We have been using it, and in many occasions we will be using this standard Gaussian integral, and that's the beauty why we have been using this Gaussian wave packet. one can propose to use some other wave packet, some ugly looking wave packet, like okay, this kind of wave packet, let's say. One can use that, but the problem is that we will be facing one problem of getting an analytical solution. How do you get the analytical solution for such a wave packet? So this can be represented, this can represent a particle as well. And but for our derivation, we are considering that it's a very nice looking this Gaussian type of wave packet which is representing the particle, because the mathematics would be much easier to deal with. This kind of wave packet, if we deal with, we have to go for numerical solution, which we will go over very soon in this class. Anyway, we have to use this standard integral, and if we use this standard integral, finally we get, I will jump one step here. You can go ahead and try to do it on your own. Just one step I have jumped here. So I'll be able to write down this integral as 1 by 1 plus 2I h cut Ta by m e to the power minus a by 1 plus 2I h cut T a by m multiplied by x minus h cut T k naught divided by m whole square plus I k naught x minus T h cut k naught square, sorry, this is I by 2m. So this is the final form of the wave packet we have. It's a different way to represent the travelling Gaussian. We are still using travelling Gaussian. Gaussian free particle. It's just another way to represent it. So if I have this now, I will assume that I'll define this alpha t. This alpha t is nothing but a by 1 plus 2I h cut T a by m. I'll define this one. And also we have already seen that xt, that's the center of the Gaussian. The Gaussian, we had this, and this was the position xt, the center of the Gaussian. That is represented by, we have already seen that this is going to be h cut T k naught divided by m. We have already seen this. So if we use these two and then plug that in here, we get the expression for the wave packet as follows. This is going to be 2a by pi to the power 1 by 4, then 1 plus 2I h cut T a by m to the power minus half, then e to the power minus, this has simplified now, alpha t x minus xt whole square plus I k naught x minus xt plus I k naught xt minus I h cut k naught square t by 2m. This entire argument we have written in terms of alpha t and xt. And if we do that, alpha t, what is the meaning of alpha t? Definitely you see this e to the power minus a x square. This is the Gaussian form. Now if something, or in this case this is x minus, in this case is going to be x minus b square. That's the Gaussian form we have. Now anything here is written a, it will control the width of the Gaussian. So it is quite clear that this alpha t is going to control the width of the Gaussian and xt is controlling the center of the Gaussian, which means I have a Gaussian, this width will be controlled by alpha t. It will be controlled by, it is not proportional to alpha t, I will show how it is related. It is controlled by alpha t and the center position, that is controlled by xt. So that is the basic idea, meaning of this, the function. So now we have this expression and we can further reduce this expression, this argument particularly, we can reduce this part of this argument as follows. I can write down I k naught xt minus I h cut k naught square t by 2m equals I k naught h cut t k naught by m minus here I have just written this xt value here, okay, xt expression minus I h cut k naught square t by 2m. So this can be simplified as I h cut k naught square t by m 1 minus half, which is nothing but I h cut k naught square t by 2m. So what we get here is that I can basically reduce this part of the argument and I can write down as I h cut k naught square t by 2m. And we have also realized that the momentum of the particle, free particle, is going to be p naught is h cut k naught, that we have seen already, the momentum of the particle, momentum of the particle. So if this is the momentum of the particle, then I can see that I can write down that I by h cut p naught square t by 2m equals I by h cut k naught square h cut square t by 2m equals I k naught square h cut t by 2m. So what we see is this part can be represented as this in terms of the momentum. So if we do that, finally what we have is following: psi Wavepacket xt equals 2a by pi to the power 1 by 4 1 plus 2I h cut t a by m to the power minus half, and then e to the power minus alpha t x minus xt whole square plus I by h cut p naught x minus xt plus I by h cut p naught square divided by 2m t. So now we have represented the free particle Gaussian wave packet in terms of alpha t, xt and p naught, that is the momentum of the wave packet. And we can further reduce it in a following way: 2a by pi to the power 1 by 4 e to the power, this part can be written as e to the power minus half ln natural log of 1 plus this term 2I h cut t a by m. And then I have this entire Gaussian function alpha t x minus xt whole square plus I by h cut p naught x minus xt plus I by h cut p naught square by 2m t. So if I do that, then I can finally express this wave function as 2a by pi to the power 1 by 4 e to the power, this entire term can be written as e to the power minus alpha t x minus xt whole square plus I by h cut plus I by h cut p naught x minus xt plus I by h cut gamma t, where I will write down all this. So this is the final expression of the wave packet, free particle wave packet. The general form, this general form will be used, where we have alpha t, and this is given here, where alpha t is a by 1 plus 2I h cut ta by m, that's alpha t. P naught is the momentum of the wave packet, h cut k naught. xt is the center of the Gaussian. So this is related to, these are related to the width, this is related, so related to width. I am not saying this is representing the width, it is related to width, this is related to but this is not related, this is directly representing the momentum of the wave packet. This is center of the wave packet which is nothing but h cut t k naught by m, and finally I have this gamma t, which is nothing but p naught square divided by 2mt plus I h cut by 2 ln 1 plus 2I h cut t a by m. So this is the general form of the traveling Gaussian wave packet, and we can see that if this is and the same form can represent a stationary Gaussian function as well, the stationary Gaussian wave packet which we have seen previously. And in order to make it stationary, all we need to do is that p naught should be 0, because it doesn't have any velocity, so it doesn't have any momentum, it is not moving at all, so it doesn't have momentum. So in this, if you use p naught equals 0, then the term which will be eliminated from here is this term will be eliminated and this term will be eliminated, because they both have p naught term, and remaining term will be there. And if you compare remaining term with the previous results, you will see that they are matching with each other. So this is the general form of the Gaussian. We'll remember this, and we will use very frequently. This is used in Wavepacket dynamics, Gaussian Wavepacket dynamics particularly. So, we have come to a conclusion or come to the end of this module 3. In this module, what we have studied, the first take home message should be from this module is that when I think of particle, immediately I get an impression that I am seeing a ball, and that should be avoided in quantum mechanics. There is nothing called particle like ball in quantum mechanics. In quantum mechanics, particle would be represented by this. Shape can be different, shape can be Gaussian, shape can be different else, something else. But what does it mean by particle in quantum mechanics? Particle is actually a localized matter wave in space. This is called particle, and this is something which we should practice. It doesn't come immediately because we are so much familiar with our daily experience that immediately once we think of particle, we immediately think of the ball, and that should be avoided. It is in quantum mechanics, there is nothing like ball. It has to be like a localized matter wave. So, this is one important point which we have clarified, and then what we have done is that we have shown different rigorous mathematical derivation, and in the derivation we have we have shown how Gaussian wave packet would propagate in time, and then finally we have got this general expression for this wave packet. General expression of this wave packet would be very useful for, and this is for free particle. This okay, I will keep some reservation. This is a general expression for free particle. So far we are calling it free particle because we are using P naught, and question is, yeah, it is for free particle. Free particle, which means potential experienced by the particle is 0. There is no force acting on the particle. So, if the force is not acting on the particle, quantum particle, it will just move with the same velocity. It will not change the velocity at all, and that's why momentum is constant. This is the momentum which is constant. Now, question is, can I use similar kind of form for a particle experiencing potential such as linear potential or quadratic potential? I will keep this question open, and I will end this session. I will meet again in the next module.